coup de volant. Un coup de poing. Un coup de pied. Un coup de pied. Un coup de pied. Un coup de marteau. Un coup de couteau. Un coup de sabre japonais. Un coup de statue. Un coup de téléphone. Un coup de téléphone. Un coup de sonnette. Un coup de sonnette.
C'est Hubert, je reconnais son coup de sonnette.
Quand Robert s'élance sur le boulevard, sans regarder ni à droite ni à gauche, on entend un coup de frein strident. On entend aussi un juron retentissant.
Putain, merde! Putain! Casse-toi! Sale con, enfoiré!
Est-ce que Robert s'est fait écraser? Est-ce qu'il est mort? Non, il n'est pas mort. Nous ne pouvons pas le tuer tout de suite. Nous avons encore besoin de lui. L'étude du subjonctif vient à peine de commencer. Robert ne s'est pas fait écraser, mais il a bien failli se faire écraser.
Je suis pas en retard, non?
Non, non. De toute façon, ça ne commence pas avant 2 heures. Tu veux qu'on y aille?
D'accord, on y va.
Allons-y.
Et ils y vont. C'est notre vieil ami, le verbe aller. Tu veux qu'on y aille? D'accord, on y va. Allons-y, ils y vont. Robert et Mireille demandent 2 places.
2 places, s'il vous plaît.
Des places de cinéma. Des places de train. Madame Bello place les gens. Elle leur indique leur place.
C'est ma place, c'est ma place, c'est ma place.
Ici, Mireille a pris la place de Marie-Laure.
Allez, Oust, rends-moi ma place.
C'est dommage que nous n'ayons pas pu venir lundi.
Pourquoi?
Parce que c'est moins cher le lundi.
L'ouvreuse attend. Elle attend un pourboire. Elle attend qu'on lui donne un pourboire. Elle s'attend à un pourboire. Elle s'attend à ce qu'on lui donne un pourboire. Mais Robert ne lui donne pas de pourboire. Il ne sait pas qu'il faut donner un pourboire aux ouvreuses. Il n'est pas au courant. Et toi, Jean-Claude, tu es au courant?
Je sais pas.
Il ne sait pas. Il n'est pas au courant. Quelquefois, c'est dangereux. Il ne sait pas. Il n'est pas au courant. Quelquefois, c'est dangereux d'être au courant. Il vaut mieux ne pas être au courant.
Comment veux-tu que je le sache?
Sache, c'est le subjonctif du verbe savoir. Comment veux-tu que je le sache? Enfin, le film commence.
Allez, Oust, rends-moi ma place.
Je te ferai un petit dessin.
Robert est mal élevé parce qu'il parle au cinéma. Mireille non plus n'est pas toujours bien élevée.
Merde.
Qu'est-ce que tu es mal élevé?
Bien ou mal, monsieur et madame Bello ont élevé 3 filles. Et ce monsieur, lui, élève des chefs de bureau, quelqu'un. Ce sont sûrement des... Elle le jette. Qu'est-ce qu'ils font? Ils marchent ou ils... C'est une ouvreuse. Morale.
Ne t'inquiète pas, je t'expliquerai. Je te ferai un petit dessin.
Ils vont pas bientôt se taire, ces deux-là? Oh là!
processing works differently. That for every single table, and you have to write that code over and over again for every single table that you are replicating from your source database. Apache Flink is an open source framework that provides support for CDC format, and that's one of the frameworks that we are using in our solution. Another challenge, as I mentioned, is we need some type of a data management in our data lake so we can distinguish the snapshot of the data from the change data captures that is stored in a small delta files. As you can guess, the streaming job writes many delta files, and those are very small files. We need a framework that compacts these small files into the larger files so then the performance of the reader does not suffer. To solve that challenge, we are going to use transactional data lake frameworks. So the rest of the presentation, we are going to dive deeper into Apache Flink and transactional data lakes, and then how we can integrate them in one solution. Apache Flink for stream processing allows us to work with a structure that is called dynamic tables. Dynamic tables are very similar to the tables that you are familiar in relational databases, but they continuously update. This is a very important concept in our solution because, as I mentioned, we want to work with a framework that understands the CDC and provides the data types that can support us in building such a solution. Apache Flink also supports a stateful computation, so when we need to join and aggregate the results, it can remember the previous result, and when it receives an update, it can update the previous result. It makes it much easier for us to do runtime analytics and aggregations to feed the downstream systems. It performs operation at in-memory speed, which is exactly what we need because we need a scalable and highly performant framework to work with the change data capture events. It does support the Debezium JSON format, which is one of the formats that you can produce CDC data. So next I'm going to talk about the transactional data lakes frameworks that can help us in our solution. As I mentioned, we need a framework that helps us with managing files on our data lake. We have a lot of small files and we need frameworks that can compact these to the large files, and also they can understand the deletes and inserts and updates. We need to implement the concepts of updates and deletes on our data lake so that a reader can always see the latest snapshot of the data and also can do things such as time travel. A reader should be able to read the same way as it would read from a streaming source from our data lake. So we need something that provides us that ability to go back in time and then read all the data changes from any given point in time forward. These transactional data lake frameworks help us. I have mentioned a few major ones here: Apache Hudi, Apache Iceberg, Delta Lake. All these frameworks provide support and connector for Apache Flink. You can use Apache Flink in combination with each of these frameworks to either write to a data lake or read from a data lake. If you read from a data lake, you would be able to set a pointer to read from a specific point in time until the latest and constantly reading as the writer job writes new files. This will help you to build a real-time job that constantly reading the data changes from a data lake and then writing it to your downstream database. Now let's take a look at the solution. So as you can guess, there are 3 different teams managing this solution. First is the data producer team, which needs to only build the pipeline for capturing their data changes and providing that as a product in Amazon S3 Data Lake. They have combination of different sources, and they want an ingestion pipeline that can capture the CDC data from all different sources and then be able to process that and send that and store that to Amazon S3. For ingesting the data, they're using Amazon MSK Connect, and they're using an open source DBZM connector on Amazon MSK Connect to capture the data changes and storing them into Amazon MSK. Same team uses Amazon Kinesis data streams for capturing the IoT device events and then storing it in Kinesis data stream. Apache Flink running on Amazon Kinesis Data Analytics can ingest the data events from the Amazon MSK and Amazon Kinesis data stream at the same time and join them together. This was necessary because the producer is the only team that knows how to enrich the data that receives from the IoT devices with the data changes that are coming from multiple sources, that are coming from multiple data sources, and then process them and send them to Amazon S3 Data Lake. In this solution, they are using Apache Hudi as a format of the transactional data lake to store those data changes on the data lake. Since the Hudi format is used for storing the data on data lake, the consumer should use Apache Hudi for consuming this data. In this case, consumer had multiple choices, but they chose a stream processing because they needed a low latency to pick up the new changes and send that into their downstream data store, which in this case is S3 Data Lake. They also use Apache Flink as it's a reliable framework for data streaming, and they consume the data changes in Apache Hudi format and store them in their downstream system. A central governance team controls the access between the producers and consumers. They need to make sure that the right people have the right access to the data. If there are other data sets in the data lake which this particular data consumer shouldn't have access, that's the job of the central governance team to enforce that access control. They have fine-grained access control through the tools such as AWS Lake Formation or the S3 or the S3 resource policies. Okay, we are going to switch to the demo and show you how this works in actual environment. I'm in the producer account now, and I want to begin with the data source. The data source is Amazon Aurora MySQL. In this MySQL instance, I have a database that consists of multiple tables. Here are the important ones: the customer, the site information, and the orders. Also, I have a Kinesis Data Analytics application which runs Apache Flink. You can have two types of Amazon Kinesis Data Analytics applications. You can have an application that is written in Java or Scala or Python, and then you package it and then you upload it and run it. Or you can have Amazon Kinesis Data Analytics Studio Notebook. A notebook provides you a development interactive environment, and this is what I'm using today because that's easier to understand and interactively explore the data. In my application, I have provided some dependencies as a custom Java archive library or jar files, so then they help me to write in Hudi format and read in Hudi format. Also, I have created this application in the same Amazon VPC as my source database, because this application should be able to privately access the database and then connect with it so it can read the data changes. These are the list of libraries that I have provided in order for Apache Hudi to work with Apache Flink. I will provide the list of these files later, so then you can also download them to build it in your environment. So let's take a look at what the application looks like. All right. This is the notebook powered by Apache Zipline and managed by Amazon Kinesis Data Analytics, and I'm using this as my data producer. So before we begin, we need to set our checkpointing configuration so Apache Flink knows how frequently it should basically store the checkpointing. And checkpointing basically is a recovery feature of Apache Flink. Should anything fail, it will resume from the last successful checkpoint. Checkpoints include information about the environment variables of each operator. Next, I'm setting up some boilerplate, for example, the host name for my database, and then the S3 URL that I'm going to write the result of the job. Next is where I define the structure of my source data. So as I mentioned, my data resides in a SQL database, and I need to tell Apache Flink what's the structure of those tables. As you can see, there are some metadata that are coming from the database itself, and this metadata is produced by the connector that I'm using to capture the data changes, or CDC. As I mentioned, CDC data has a lot of information with it. For example, the database name, what was the original table name, what was the operation timestamp. I'm interested in that data, and Apache Flink can parse that data and understands that data. It provides a native service for it. That's why I'm using a mapping to be able to ingest that data into pipeline as well. And these three are the original columns in the source table. I'm using a MySQL CDC connector, which I provided the Java archive library in my custom libraries part of the application. And I will provide the reference link for that. So you can basically ingest the CDC data the way that I use today without the use of Amazon MSK Connect. If you remember from this slide, I'm using Apache Flink itself to ingest the CDC data without the help of Apache Kafka. The rest are the configuration that is needed for connecting successfully to the data source. I repeat the same step for other tables, for example, the customer site and sales order table. As you may notice, this is very similar to familiar SQL structure that you used to work. And this is one of the benefits of Apache Flink, because you can work with the streaming data using the SQL syntax, which makes it very easy. So in order for me to test everything is working, I have a simple select query that selects the data from one of these tables. Ideally, what should I see is a table that shows the latest snapshot of the data, and then if I update a record, I will see that record changes here in real time. So you can use this as an experiment in your environment, and you can run this query and update some records and see what the result would be. Next, I need to define some tables that also point to the product that I'm building on S3 Data Lake. So I created 3 tables, one for customer, one for customer site, and one for sales order. And I appended underscore hoodie at the end to distinguish the name from the source. These tables have information about what original table they're coming from, what's the record time, what's the event time, and then the other columns that match what we had in the source. I also want the data on S3 to be partitioned based on the customer ID. Partitioning is important when readers want to read the data to be able to filter the number of the files that they need to scan. The rest are Apache Hudi configuration, and if you need more information on what these options and configurations are, I will provide a reference for you to read more about those. The main important thing here is that we need to provide a path where this Apache Hudi data source is going to be located and where our streaming job writes its data. Another important option here is we define the table type as merge on read. Merge on read means that the writer can write with a low latency, and then the compaction will occur later in an asynchronous mode, and it will compact the small files into the larger files later. Same configuration exists for other tables, except that the URL has a different location at the end that writes them in a different location in the same S3 prefix. So now that the job knows where to get the data and where to write the data, it's time to write the job itself. I have left a few insert SQL statements here for you. If you want to explore it and if you want to run it, you can do it. And you can go through the same steps in your own environment. But for the sake of demo today, I'm going to run one of these insert selected statements only, which is reading the order data from the MySQL database and then writing them on Amazon S3 in Hudi format. When it does that, it also does a very small transformation, which concatenates the database name and table name and adding a dot in between, and basically storing that as an original table name in our Hudi format. Okay, so let's take a look at what happens when we submit this job. When you run this SQL statement, this notebook interprets this as a streaming job, and it submits that as a streaming job to Apache Flink cluster. When I go to Apache Flink dashboard using the provided link on the notebook, this is what I usually see. Each of these blue boxes representing a task in the streaming job. I will zoom out so you can see all those blue boxes, and I explain a few of them just so you know what is happening here. So one task is responsible for capturing the change date event. Another task is responsible for determining how these events should be aggregated with each other and then constitutes a single file. The stream writer consists of multiple tasks which run in parallel to write these files on Amazon S3. And at the end, these are the compaction tasks that they run with a certain frequency to compact the small files into large files. So you can see a lot of these complex tasks have been just compiled and submitted by Apache Flink SQL API. So with a simple SQL query, I was able to build a relatively complex job, which is helping us in building and maintaining data replication pipelines in a very easy way and maintainable way. Let's verify if this is working. So here's the location that I'm